All right, continuing on, I would like to assign a probability to the planet being in the habitable zone of the solar system. And so I'm going to make that 1 chance in 5. Okay, why? Because 1 astronomical unit distance is the distance from the Earth to the Sun, but the span of the habitable zone is probably not much more than 1 astronomical unit, either in front of or behind the Earth. And if we compare that to the size of the solar system as a whole, that's a small fraction of the size of the solar system. So I think that this is a somewhat generous estimate as to the planet being in the right distance away from the Sun. I'm going to call this 3A because there's actually also a 3B that has to do with the habitable zone. The planet and the solar system have to be at the right distance away from the center of the galaxy. And so this is the galactic habitable zone. Okay, and so in the galaxy, the solar system can't be too close or too far away from the center of the galaxy either. And so it just turns out that our solar system happens to be about 28,000 light years away. And the total size of the solar system is about 100,000 light years. So this puts us maybe 3/5 of the way out from the center. And so if we crudely then think in terms of the habitable zone as being something that encompasses our solar system and extends out on either side by maybe 10,000 light years or so, then we believe that this is what we could call the galactic habitable zone. Why? Well, if the solar system is too close in, let's say it's in here, then it will experience violent explosions from supernovae blasts. Okay, so too close, you get too much radiation, and also at this close of a distance, there's too much iron in the disk that forms the solar system. Now, why is that an issue? Well, the amount of iron that forms in the core of a planet affects how quickly the planet forms. And so if you had a planet, let's say like Jupiter, that had more iron in its core because there was more iron available, then that planet would form too quickly, would experience drag from the disk of the galaxy, which the disk of the solar system within the galaxy, I should say, and it would spiral inward, just like Jupiter did before Saturn pulled it back out in our solar system. But it would do it much faster because the planet would form more quickly with more iron in the disk. And so with too much iron in the disk, then Jupiter-sized planets take out all the inner planets before they ever have a chance to form. So you have too much radiation from supernova blasts, and it's much more probable in here closer to the center of the galaxy that you'll have more stars and therefore more supernova explosions. But you also have too much iron in the disk because iron is formed in those supernova explosions. And so the remnants then of the planet will, the remnants of the explosion will then form planets. Okay, and so this is the reason why you can't be too close to the center of the galaxy. What about too far away? Well, then there's too little iron. in the disk that makes up the solar system. If there's too little iron, you have the planet's not forming fast enough. So here they form too quickly, here the planets form too slowly. So what do we mean by too slowly? Well, the sun ignites, the planets haven't formed yet, and so the sun just blows away the gas before the planets can ever form. So you don't get a solar system. So if we have a planet and a solar system forming too far out from the habitable zone, farther out than the Earth formed, from the center of our galaxy, 28,000 light years, then it's the opposite problem. There's too little iron. And so we have to be at just that right distance away from the center of the galaxy as well. So let's assign a probability to that. Let's say 1 chance in 2 that the planet is in the habitable zone. Now eventually we're going to be multiplying these probability factors together to get a total probability. But for the moment, we're just kind of randomly assigning values for these different probability factors, and when we're all done, we're going to multiply them together to get the total astronomical probability. Okay, so let's move on. Let's go to number 4. We have to also, for forming a planet, that planet needs to orbit a star that's not too big or too small. So in other words, a star that's very much like our own sun. And so this may sound a little bit narrow-minded to say that it's got to be the same size as our sun. But let's see what happens if the star is too big. If the star is too big, we have this expression in astronomy that deals with stars. For big stars at least, it's live fast, die young. Okay? And so these big stars then burn themselves out quickly in just a few million years. Okay, now quickly, from our point of view, is different from an astronomical point of view. So a few million years seems like a lot of time to us. But when we compare that to the billions of years that our solar system has been around, a few million isn't much at all. And so it's maybe less than 0.1% as long as our sun has been around. Okay? And so if it burns out quickly in a few million years and explodes, then that's the end of life in that solar system. So life would have to develop then within a few million years. And the evidence is that life didn't form nearly that fast on Earth. So if we use the Earth as a guide, it doesn't look like planets that are orbiting around really big stars are going to contribute much to the number of extraterrestrial civilizations. What if the star is too small? Well, you'd think that you could just move the planet in closer, and you could move it into a nice distance away from that star, and that everything would be fine. But it's not, because of tidal forces. If the star is too small, then the planet is too close. And just like the moon, as it goes around the Earth, keeps its same face pointed toward the Earth, this planet will keep its same face pointed toward the sun by tidal forces. And so if that happens, then one side is going to get cooked, the other side is going to freeze. And so although stars that are smaller than our sun will live longer, it creates severe difficulties in terms of habitable territories that can exist for a planet to have that planet orbiting a star that's too small. Because the only way it can be within the habitable zone, which is necessary for it to have advanced life, then it has to keep its same face pointed toward the star, which is not good for having many habitats that are favorable. You would only, in a small shadow zone between the near side and the far side, have a situation where the temperatures were just right for life. So I'm not saying that it's impossible for this to happen, but it lowers your chances quite a bit. And so for a planet to orbit a star that's just the right size, let's just be optimistic and say 1 chance in 2. This may seem like it's too optimistic, but maybe there are other ways to make advanced life that we haven't thought of. And maybe there are even other forms of advanced life that we haven't thought of. So I'm trying to be generous with these probability estimates, even though it may seem like these estimates are a little too high considering how specialized these conditions are. And then finally, I'm going to put here miscellaneous, which is basically everything that we haven't thought of or haven't mentioned. And I'll give you a few examples of what these things could be. Having a moon. The Earth has a moon that stabilizes the rotational axis. We have a Jupiter-like planet in the solar system. Only about 10% of solar systems have a Jupiter-like planet in their solar system, and we think that Jupiter was necessary to deliver the right kind of elements to the Earth in the early part of the solar system, and it also clears out the solar system of harmful large asteroids and comets that would be smashing into the Earth all the time. So Jupiter's like a policeman in the solar system that keeps everything in order. The Earth has a crust that's just optimum for conducting heat. Venus doesn't have that, and so Venus has catastrophic volcanic eruptions and doesn't have an even flow of heat from the interior. The Earth has plate tectonic motions, and those don't seem to be automatic. As we saw, the Earth is the only planet in our solar system that has plate motions. So if you consider all of these things, I would say that the miscellaneous factor might be 1 chance in 100. And so that includes everything else that we either haven't mentioned or haven't thought of. Okay, so if we want to put this all together then, we can say that the total astronomical factor almost got that. Would be the product of these individual probabilities. Okay, and so we have number 1, planet is right size. I have 1 chance in 2 for that. Then planet made of the right materials, 1 chance in 5. Planet at right distance from the star, 1 chance in 5. Planet at right distance away from the center of the galaxy, 1 chance in 2. And then planet orbits a star, not too big or too small, 1 chance in 2. Miscellaneous factor, 1 chance in 100. And so you can see that I could have put a lot of different numbers in for each one of these. And so the numbers themselves aren't that important. But what is important is that the overall number, I think we can all agree, will be a small number, which means that regardless of the exact value for that number, it's going to tell us that it's very unlikely for a planet to have all of the appropriate astronomical conditions. So here then, 100, that's 1 chance in 200, 400, 1 chance in 2,000, 1 chance in 10,000, that's 1 chance in 20,000. So what does that mean? Well, 1 chance in 20,000 tells us that if you were to randomly survey a planet, a whole bunch of planets, that only 1 time in 2,000 would you find a planet that is as favorable for life as the Earth. We're not going to take this number too seriously, other than to say it's a small number. But let's just imagine that it were correct, then the meaning would be that if you randomly survey 20,000 stars, only 1 time out of 20,000 would you find one that is as suitable for life as the Earth is. And so what does that tell us? Well, it tells us that on the average, we're going to have to go a long way to find a planet that is Earth-like, because planets aren't that close to each other as it is, but if you have to go through 20,000 of them before you find one that is Earth-like, then the odds are those planets are probably very far away. That means that if there are extraterrestrials, they would have to travel an enormous distance to get to us. Okay? And so that is all implied by this. ETs have to travel a large distance to get to us. And so this may be what has saved us in the past from the interference of extraterrestrials. On the other hand, some of you may believe that extraterrestrials are visiting us every other Tuesday, but we'll see a little later on that that statement is not justified by scientific fact. And so we'll talk about what that means in terms of a scientific analysis of the UFO evidence later. But this gets us through the first part of our Drake equation solution, which has to do with a habitable planet.